So welcome everybody to today's class. We're going to start with an introduction to reinforcement learning, just a little bit of background. And then we will actually look at a simpler, conceivably simpler problem, the K-armed bandit problem, in order to understand the importance and one of the crucial features of reinforcement learning algorithms, the exploration versus exploitation trade-off. So reinforcement learning is a subpart of machine learning. Now, machine learning has two main areas that are usually considered. One is the classification problem or supervised learning, and the other one is clustering or unsupervised learning. So a lot of machine learning applications or problems are classification problems where you're given a training data set that includes labels, and then you have to find the correct model in order to generate the labels for the training data, but more importantly for the unknown instances that you haven't seen yet. So one example of that would be if you want to train a computer vision system to detect dogs, then you may present it with a whole lot of images, and some of them have a dog in it and some of them don't have dogs in it, and then you will manually, or somebody must label the images, must label the training data saying, oh, this is a picture with a dog, this is a picture without a dog, so on and so forth. And then you apply your machine learning system in order to derive a model that is then able to predict dog or not dog on images that the system hasn't seen yet. It's very important to realize that the training data in the classification error, or the error on the training data, is basically meaningless, right? Because you told the system this is a picture of a dog, then when you show the same picture again to the system and it says this is a dog, then that's hardly impressive. Like a database could do that. The crucial feature of machine learning is that it is able to generalize from the seen labeled training data to unseen instances. Clustering is another type of machine learning. It is the more difficult problem in general because you end up having to, you don't have any labeled training data. So you're simply given a list of Mohan 1, I have to block you because your microphone is on and it's too loud. Clustering, you simply give us a collection of data to the machine learning system and basically tell it that I don't understand how to organize this, maybe you can figure it out. Because the training data is not labeled, that is usually the harder problem, the more difficult problem. And reinforcement learning is another area of machine learning that is sort of in the middle between those two, because there's some labeling of the training data that we provide through the reward function, but we don't specify the exact reward that needs to be assigned for each state. Only partial state. So it's sort of mostly unsupervised training data, or mostly unsupervised machine learning that we apply. So the whole point of reinforcement learning is to try and make good sequences of decisions. The system has to generate sequences of actions for an agent, and then at some point during the performance, there will be rewards presented to the system, either in the form of well done, like positive reinforcement, positive rewards, or also we could have negative rewards saying, oh, this was a bad move. And this whole training regimen, the whole machine learning setup, is done under uncertainty. And in particular, one of the things that we have to figure out as well is we need to act in the environment. So we want to exploit the knowledge that we learned, but also we don't know the full extent of the environment. So we have to exploit the knowledge, explore the environment in order to actually learn about the domain. So some of the examples of reinforcement learning where it has been applied to great success is in various games. So the deep brain system was able to apply reinforcement learning in order to learn programs that can beat the world champions in chess and checkers and Go and all other adversarial games. In there, the environment is the particular game. So chess, for example, the actions that the agent can do are the legal chess moves that while it's playing for white or black, the moves that it can make on the board. And the reward in this case is simply at the end of the game, you either win, so you get +1, or you lose -1, or you draw 0. And those were the only information that were given to the system. Based on that, the system actually learned to play world-class level of chess and Go and checkers. Also, one of the, I think, very interesting projects with reinforcement learning were the Atari game set. So OpenAI was able to train a reinforcement learner to play many of the classic Atari arcade games like Breakout and Space Invader, so on and so forth. And the computer learned how to play the game by just watching the screen. The reinforcement that the system received, the reward that the system received, was based on the score. So if the score went up, then that was a positive reward. If the score went down, that was a negative reward. Or if the player died, then that was also a negative reward. Or I guess if you completed the game, finished the entire game, then that was also a positive reward. Robotics motion planning. Now reinforcement learning is a very hot topic in that particular area. Programming good motions for a robot to perform certain actions is a difficult problem. So it's very enticing. It's very nice if you're able to just train the system rather than having to program it. So if you cannot figure out what the correct actions are for your robot to balance the scooter while driving, then maybe you can have the robot try various things and learn by itself how to balance the scooter while driving it. Natural language processing, translating of sentences, building semantic structures can also be based on reinforcement learning. And also some areas, some algorithms for computer vision are now based on reinforcement learning. At the beginning, I talked about detecting cats and dogs, for example, using an image. That's still by far the most common setup, but it requires a lot of training data, and somebody has to label all these instances for supervised learning. So there's a lot of interest in doing computer vision now unsupervised using clustering. And if you can combine that with a specific performance task that the system can achieve, then you can also use reinforcement learning in order to solve your computer vision problem. So one example of that would be Theta Fox implemented a system where in order to do SLAM, simultaneous localization and mapping, the features that the vision system needed to track in order to localize the robot, in order to map the environment around the robot, those features were actually learned using reinforcement learning. So the computer vision system would not be programmed saying, oh, you need to look for corners or edges or tables or chairs or walls or doors, but it was asked to drive around in the environment, and then you would constantly ask it, where are you? And is there a door nearby, basically? And if it answered those questions correctly, then it would get a positive reward, otherwise a negative reward. And then it would derive the features in the computer vision system that would allow it to do the correct prediction for localization, position of the robot, as well as the map around the robot. And one problem with this reinforcement learning approach is that it's sort of learning while running, right? We start the robot out in the environment and we expect it to play chess, or we expect it to drive our scooter, or we expect it to navigate and deliver a letter to the oh, yeah, the question. Okay. Yep. Hello.
All right. Thank you. Sorry about the noise earlier. I'm not sure exactly how does really reinforcement learning, how does the system of negative and positive rewards really differ from weight adjustments for a classic machine learning model? I don't understand the exact difference.
The rewards, the main difference with the reward is that they are actually delayed. So the weights that you use in a neural network, they just are used during the computation, right? And then they generate an output, cat or not cat. right? So the weights in your, let's say you're training a neural network, then you give it a whole bunch of images of cats and not cats, right? Or cats and dogs.
Yeah.
And then you adjust the weights in your network so that when you see a picture of a cat, it's more likely to produce the answer cat.
Yeah.
Now, the rewards, you don't tell the system that it needs to know about cats and dogs. You put the robot into the world and you give it the task of bringing your dog home, right? So then it can use whatever machine learning system it wants to. It can use whatever decision algorithm it wants to generate. It can use a neural network or anything else. And it drives around in the world and picks up different things and brings them home. And then you say, oh, this is a rat. No, this is wrong. And then some other time later, it brings a dog. And you say, oh, that's correct. Yes, that's what I want. That's a dog. So the weights are the internal mechanism that is used by the network. The weights determine the pattern of actuation across the network in order to generate a decision, and the reward signal is not really based on the computation. It is something outside of the agent that is generated by the trainer or the environment that tells you some of the agents that you did, some of the actions that you did in the past, they were good or they were bad.
Okay. Okay, I see.
Yeah.
Thank you.
Hello.
Yeah. Hello.
Professor, someone said he cannot enter the voice channel here. Can you add him?
Who?
I will type his name in the text here. See
his. I need his Discord ID. Did he register? Like bang register?
Yes, he said he just registered.
Yeah. Okay. Then he should be able to see it now. Okay. That command went through. I mean that student is just registered. Can you ask him now? He should be able to see the. Let me check. Yeah, he's in the reinforcement learning group. But he hasn't shown up yet. But he should be able to see the voice channel now.
I think he's in.
Yeah, now he joined, yes. I can see him now. Yeah. Or actually, maybe to make that more clear, we will talk first about the grid world and then about the K-armed bandit problem. That will also work. And wait, I will share the slides. Maybe I make a smaller one. Make a separate one. So let's first set up an environment, a very simple one, but one that's been used extensively in reinforcement learning as one of the benchmark problems. And then we'll go into the details of the exploration versus exploitation trade-offs. So the model, the basic model that we're using is in reinforcement learning is called the Markov decision process. (2110) will it be 04? Da, da, da. So definition of a Markov decision process. We assume that we have a simple agent that acts in the world. And it executes an action, and then the environment, based on the action that the agent executed, the environment changes. So if the robot, I think there's another one. if you just joined for reinforcement learning, then join the reinforcement learning text and voice channel. So the agent executes action in the environment. The environment sort of reacts, or things happen in the environment. And that in itself wouldn't be enough to actually allow us to train and pick good actions or bad actions. So we must receive some sort of reward signal at least sometime during the execution of the agent. And then the resulting system is called a Markov decision process. So a Markov decision process can be defined by a set of states S, a set of actions A that the agent can execute, a transition function that specifies if I'm in state ST and I execute action AT, then what's the probability that I end up in state ST plus 1? So sometimes our environments may be deterministic, in which case the transition function would be a single state. But sometimes our domains are probabilistic. If the robot executes a turn 10 degrees command, or step 10 centimeters to the left command, then often that command will succeed, but sometimes it'll fail. So let's say the commands that we send to the robot fail with 2% probability, then our transition function is not deterministic anymore, because with 98% probability we will end up in the target state that we would expect, but with 2% probability the action will have failed and we stayed in the same state, that sort of thing. We also have a reward function that says if you're in state ST and you execute action AT and you end up in state ST plus 1, this is the reward that you get from the environment. We have a start state S0, discount factor gamma, and horizon. So I'll talk about the discount factor or horizon later on, but on the right hand side here, that graphic is sort of the basic framework for Markov decision processes. So we have our agent. At time t, it executes action AT. That goes to the environment, and then the environment, the agent will move into state ST plus 1, and it will receive a reward RT plus 1, which could be 0, so could be no reward also, but at some point during the execution we end up with some reward signal. So I want to build a simple world in where we can try out some of these ideas to make them more real in a sense. Let's see if these guys joined now.
Professor?
Yep.
Just asking, will you share the Google Colab at the end?
I shared it already. I thought I shared
Oh, you
it.
did?
Yes.
Maybe but
In the reinforcement learning text channel, Markov decision process, the last message thing.
yeah, thank you.
Yeah.
Hello.
Yep. Hello.
Hello, Professor. Can I ask that how to define the probability how to define the probability, transition probability?
That depends on what your environment actually is. If you're dealing with a physical environment, let's say you have a real robot moving through the world, right? In that case, the transition probability sort of would be defined by the physics of the world, right?
Yes.
So, yeah. Now, we will look at different types of reinforcement learning. You are, in a sense, correct in sort of bringing this up because this transition probability, this function, may not be very straightforward to implement, may be very difficult to implement, right? It would require simulating the robot. That is actually not strictly necessary for reinforcement learning. As long as you can sample that transition probability, then there are reinforcement learning algorithms that can sort of learn this transition probability function themselves. So you don't need to have an exact transition probability. Of course, in other domains, the transition probability is very easy because when you play chess, for example, and you say you want to make a move and it's a legal move, then that move is going to succeed 100% of the time. So the transition is going to be deterministic. It is more difficult if you are dealing with robots in the real world and you have to deal with noise in your actuators and your sensors. Right. So let's have a look at the grid world. The grid world is a very simple world for our robot. It is a simulation of a small robot that can move up, down, left, and right. So it can only go in those 4 directions. And the world has obstacles in it. So they are marked in blue here. So those are spaces that the robot cannot move to. If it were to try and, let's say if it's at A1 and it's trying to move right, then the command simply is going to fail and the robot will stay in A1. And if it's trying to move up, then it's going to fail and it's going to stay in A1. And if he's trying to move left, then he's going to move to A0. And if he's trying to move down, then he's going to hit the wall and is also stuck. Now, some of the cells have rewards attached to them. Yeah, I guess that's because we're in Taiwan. So positive reward is red and green is sort of a negative reward. So if the robot enters into cell C2, he gets $72 virtual dollars. And if he enters into E9, he gets $53. But if he enters into E8, if he enters here, then he has to pay $88. Or D8 has to pay a penalty of $4, and D2 has to pay a penalty of $27. So this cell is not, this domain is just generated randomly. The robot starts in location C9 for every episode, and then it can drive around. When the robot enters into one of the green cells or the red cells, then the episode terminates and the robot is brought back to C9. The end of the episode is what's called the horizon. So in our definition here, this horizon H is basically for how long, how far are we going to run this experiment? When does the experiment end? So here it's not a fixed state. Whenever it reaches one of the green or the red cells, whenever it gets a first reward. Other times you may have a horizon that is, let's say, we're definitely going to run it 100 steps, and then we'll see what our current state is, for example. Chess, checkers, those kind of games, they also have a variable horizon, right? Because you may win or lose after 10 moves or after 30 moves. So in that case, the horizon is basically how long do we keep playing the game? Well, in chess, checkers, you play the game until the game is finished. But then there's nothing else you can do after that. So then you have a variable horizon. Robots in the real world, they could run for, let's say, 1,000 steps and then finish the episode and be brought back, for example. For robots, there's often not the exact cutoff point at which you say, okay, now the episode has finished. But also when we trained our robot on trying to learn how to drive the electric scooter, in that case we also have a variable horizon because the training would continue until the robot fell over, right? So we keep driving, and after the system learned how to control the scooter, it wouldn't fall over anymore. So then the horizon was sort of infinity. But if it made a mistake, it will fall over, and then the episode would be terminated. So I already wrote the code in order to generate the grid world. You can try it out yourself. That's a good exercise in Python programming. But yeah, let's here. I just generate a random environment where first we generate a set of obstacles and then we generate a set of rewards. and coordinates where that reward will be given. So the environment has height and width, that many obstacles and that many rewards that I want to distribute throughout the environment. And then I just generate a coordinate for an obstacle, x and y coordinate. And if that's not already an obstacle, then I set it as an obstacle, I remember it. And similarly for the reward coordinates. And then I also generate a reward signal from randomly between -99 and 99. And then I return the height of the obstacle, the environment, the width of the environment, the set of obstacles, and the reward coordinates together with the reward, zipped together with the reward. So here, each one of the blue cells, each one of these that is blue will be in the set of obstacles, and it'll be recorded as y coordinate. So 0, 1, 2, 3, 4, 5, and x coordinate from 0 to 9. And similarly, the rewards have the coordinate as well as also the amount of reward that we hand out. So $72, $27. Virtual dollars, like you don't really get dollars if you drive in there. But I think maybe this particular environment is a little bit too complex, so I'll make a simpler one in a second. So here's a function then that draws that environment using matplotlib. So we extract the height, the width, the obstacles, and the rewards, which is the definition of our environment. We set the reward coordinates for the rewards, then set up the axis sort of canvas that I can draw on, and then plot the row coordinates and column coordinates, like the header on top. And then plot either an empty, a white cell, or a white cell, or a black cell. That's a white background, that's the black outline of the rectangle that I want to draw for the value function, if I have a value function. I'll show you the value function later on. And then here we plot the obstacles. And then for the rewards, the coordinates of the rewards, if the reward is greater than 0, then it's red color. If it's less than 0, then we have a green color. And otherwise, if it's equal to 0, then it's no color, like white. That'll be filled in. And then those two functions allow me to generate a random environment and also draw the environment. So now I just have to make sure I actually executed those cells. So let's not make it so complicated. Let's just make it a 4 by 5 environment with, let's take 7 obstacles and 2 or 3 reward cell. Oh, 1 reward cell. 1. 2. 1. Okay, then let's see what we get. Okay, one student joined the wrong channel. I can bring him to the right channel. Okay. Good, so Hao Trang Lo, you're in the right channel now. And yeah. So now here I have some other functions that we'll use later on. Right now they're not important. They actually allow us to do path planning later on. Okay, now if I start at A0, I cannot reach the target. So let's take some fewer obstacles.
Hello, Professor.
Yep.
I would like to ask that if the environment is unknown, or the usually in reinforcement learning that the environment is given by us.
No. The environment for the agent is unknown. The agent doesn't know the environment. I only need to know the environment so I can show it to you and draw it. But the agent doesn't know the environment.
Oh, okay.
Yeah. So yeah, so now we have an environment here. If we reach B1, we get $37. Anywhere else we go, we don't get any reward. And then let's see. So let's think about this kind of an environment, the grid world. Start position, in this case A4 would be nice, so we would start here, but could be any other white cell. So for this kind of environment, what would the set of states look like? How many states are there, and what do they represent? So what are the states? Or how many states are there? Post your answer in the reinforcement learning channel. In the text channel, ten. No, I get 4, 15. Okay, the states, what do the states represent? The states represent the position that the robot can be in, basically in the world, in the environment. So in this case, that means every white cell or red cell, I guess we can count the red cell as well, would correspond to one state. So D0, D1, D2. D3 is not a state because the agent cannot possibly be on top of the obstacle. So D0, D1, D2, C0, C2, C4, so far all the way up to A4. So I think if I counted it correctly, that's 15 states. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. 15 states. Okay, what are the actions? And how many of those are there? 4, yes, correct. Left, up, down, right. That will be the most natural way of representing this. Now, some of them, it sort of depends on how you want to model that. Of course, not every cell can execute all of the actions successfully. So, for example, if I'm in C2, if I'm here, then the only thing I can do is go up or go down. Right? I cannot go left because it would hit an obstacle, and I cannot go right because I would end up hitting an obstacle. So conceptually, there's two ways that you can model that. One would be if you want a completely deterministic domain, then you would have to have a set of actions associated with each state. So that, for example, you would have C2 only up and down, and B2 would have all 4, up, down, left, right. And C4, this one here would have all 4 states, and this one here would have only 1. It can only go down. So you would have C4, the only action accessible would be down. That's usually not done because then you need to put all that knowledge into the system already. The more common approach is to simply have that action fail, and then make it a probabilistic domain. In practice, it won't matter much. It doesn't make a big difference. It's more a theoretical difference in the way that you describe your domain. If you want to say that every action always succeeds when it's executed, then you have to limit the actions to make sure that you only allow those that are legal for every state. But that's a lot of extra work. So because reinforcement learning by its very nature is a probabilistic algorithm, we're sort of dealing with probabilities anyway. It's easier to have a probabilistic transition function and then have actions sometimes fail. So transition function. What is the transition function? That are molded. Yes, correct. It would be the probability of successor states for each state. In general, but here I can be a little bit more precise because I have given this this domain. So for example, the probability of going into let's say C2, given that I'm executing up in state B2 would be equal to, oh, I've already typed it. So if I'm in B2 and I go up, then what's the probability that I end up with in C2? So if I'm in B2 and I execute command up, what's the probability that I end up in C2? Yeah, 1.0. Correct? And what's the probability that I end up in B3 or B1? 0, that's right. And probability of ending up in C1 if I execute left in C2. No. What's the probability that I end up in C1 if I execute left or in state C2? Yeah. That's 0 because C1 is an obstacle. So I have to set that up for all the states, right? All the transitions. Then that way I could describe it. Now that describes the one type of robot and one type of robot domain. It's important to realize that this is not the only type. Later on, we will say, oh, what happens if your control is bad and your robot, if you tell the robot to go up, there is a 75% chance it'll go up by 1 square, but there's a 25% chance it'll go up by 2 squares if it can. Then the transition probabilities would change. Even though the figure here would look the same, but the actions of the robot would be different. So this is what we have so far. Now, it's important, one important feature of the reinforcement learning is that the transition function may be unknown to the agent. But it must be static. It must be, yeah. So basically, if I have a grid world like that, or any kind of world, and I'm trying to train my agent on it, then the agent can basically learn what the transition function is. That's called Q-learning. That works very well. But what we cannot have is that the transition function changes drastically over time. If there's a slow change, I guess that would be okay too, if it's mostly static. But if you're trying to learn how to navigate in this environment and obstacles are appearing out of nowhere and then disappearing, then it would be impossible for the agent to learn that environment. Right? That's basically like creating a new environment every time. So the robot takes one step and then all the obstacles shift positions. It would be impossible to learn anything for how to navigate in that particular environment. Now, another important feature of Markov decision processes is the Markov property. So this is usually expressed as saying that the environment is Markovian or you can say the Markov property holds. True. That's saying the same thing. So what that means, you can see in the definition here for our state transition function and our reward function. Here, that state transition function defines where the next state, what the next state is, so the probability of getting into the next state, st plus 1, given st and at. So it only depends on the previous state. Right? Similarly, for the reward function, it only depends on the previous state and then the action that we execute and the domain, the state that we end up with for the reward. But here, previously, it's only one state. So that is important for sometimes you want to have a domain, you want to express a domain where the maintaining the Markov property may not be so intuitive. In that case, you have to be careful. You have to think more carefully about the way that you phrase the problem. So, for example, in the grid world, it's fairly intuitive to assume that if I'm in state B3, it doesn't matter how I ended up in state B3, right? It didn't matter if I go A1, A2, A3, B3, or if I went A1, A2, A3, A4, B4, C4, B4, B3. The only thing that matters is that I'm right now in cell B3. Then that domain has the Markov property. That domain is Markovian. So the history doesn't matter. The only thing that matters is where you're currently, what location you're currently in. Now, if I have a domain, like we did a problem or a, yeah, I can actually show the video. So some of the first robot projects that I did was using toy cars, remote control toy cars, and we took the remote control and connected it to the parallel port of the PC. So you know how long ago that was, because I haven't seen a parallel port on a computer in 20 years, maybe 15 years. So it's been a long time. But yeah, that time laptops and PCs, desktop machines still came with parallel ports, which was nice because you could turn bit signals on and off. So you could read some digital input, you could generate some digital output. So we connected it to the remote control, and then that meant that the PC could control the toy car. And we had a camera, a Global Vision camera system that was mounted on the side, and it was overlooking the playing field. And then here's our robot driving, and it had to drive a letter, because that was at the University of Auckland. So we made a letter A-shaped racetrack. So it started from there to there to there to there, and then up to the A. So for the University of Auckland. So here's our toy car driving, and it does a pretty nice job, actually. So it just does laps and laps after. So this was actually done using a reinforcement learner that nowadays you would call it sim2real, because we trained it first on the simulation. After we had the simulation, we tuned it driving the real robot car. But the problem that we had was when the reinforcement, one of the issues, and we'll get into that in more detail throughout the class, but when you're dealing with robotics, one of the problems is that the set of actions is sort of infinite, because you can define steering angles, right? 0 degrees, 0.05 degrees, 1.3 degrees. So the steering and the velocity control for the car is a continuous variable. So you sort of have an infinite set of actions. That makes it harder than the grid world, where we only have up, down, left, and right. That's much easier, right? We don't have go off at 5 degrees, 7 degrees, 7.2 degrees. And the other problem is that your state is also not discretized, right? Similarly, because you could be your x and y coordinates and angles are all continuous variables. They're not like you're in cell B1 now or you're in cell B3 now. So dealing with real robots and reinforcement learning, that is always a tricky problem, or it can be a tricky problem. with the other problem that we had though was with the driving, when you see here, okay, this one it did well. That was the first lap, so it was a little bit slower. Now it's faster. And now you can see how it oscillates on the control. Like, it's a straight line, but the robot drives, it oscillates left, right, left, right. So what we wanted to do was set it up so that we would prefer to have, and that makes the car unstable and makes it hard for the vision system to track the car. It's much easier to track objects that are moving in straight lines in the vision system than objects that move left, right, left, right, left, right. So what we wanted to do was reduce the amount of work that the controller did. So we wanted to have a smooth control. So we didn't want to have left, right, left, right, left, right. We wanted to have go straight, even if you drift off, then left, and then go straight again. So we wanted to have a smooth control. That, however, would mean that the domain now is not Markovian anymore. Because if I look at this picture then, and I want to say whether this was good or bad, right? That's basically what we have to do for the reward function. Then you can see, you can sort of think about the fact that, yes, our reward, we can assign a reward based on how close we are to the racetrack, or how fast we did a particular loop. But the problem is DC. What's DC? Deceased. No, my stream should still be running. Okay, anybody else can still hear me? Okay, thanks. Okay, good. So WikiLeech, that seems to be just you in this case. Okay, so what we wanted to do was, instead of just looking at the error, how close we are to the correct racetrack, we also wanted to use how smooth the control was. But in order to be able to do that, then it would make a difference on how we got into the state. Because if I look at that picture now, in order to assign the reward, not only do I need to know where that robot is with respect to the racetrack, but I also need to know how the path was, because no, the state is not, we have a continuous state space in this case, which means we use a function approximator, a neural network we used at that point in order to approximate the state space. So it's true, yes. With robots, it's always harder because you have a continuous state space and you have a continuous action space, almost by definition when you're dealing with robots. Okay. So let's look at the domain. But what I wanted to talk about now was that wait a minute. Here, if I now include the amount of steering control I did, which means the amount of left-right command that I send, that would be an obvious way in which we can smooth out the control. Then you can see it's not Markovian anymore because I have this picture, but I don't know if the robot followed the blue path, which would be very smooth, very nice, or it followed the red path. So in this case, it is not Markovian anymore. Font color white. Right. So that would be a problem. Based on Markov, who is a famous mathematician, and it means that transition function, transition and reward functions only depend on previous state, not the history of how you got into that state. So if you're currently in state 92, that's all I need to know in order to calculate the reward and the transition function. I don't need to know if you went through states from 0 to 92, or if you went 0 and then 92 directly, or if you went to some other states first. So the history of how you got into a particular state is not important. Then your domain has the Markov property. And if it doesn't have that, then it's non-Markovian. Where's my... Now, in our case, it actually still worked, but none of the proofs for reinforcement learning would be applicable anymore. Okay, now I have my... I just have to reload it quickly. Come on. Da, 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 da. Okay, let me exit the page. And then hopefully it can... Oh, now I have to rerun the whole thing. Yeah. Okay. I don't know why this is so slow now. Can anybody still hear me, or am I off the internet now?
I can hear you.
Okay, then why is Google Colab not talking to me anymore? Okay. What's going on now? Okay. Oh, come on. Okay, so all I wanted to show was that image basically. Markovian means if I see the picture, then I know what the state transitions are and what the reward is that I need to hand out. If I take the path, the history of how we got there, if the amount of control that it did in order to get there, then it's not a Markovian domain anymore. So none of the proofs of convergence for reinforcement learning would be applicable anymore, for example. But now my edge died. So I think I have to reboot the browser quickly. So let me do that. Oh, maybe. Okay, so I have to reboot the browser. Yeah. I'm gonna leave that one. Okay, let's hope for the best. Okay. Oh, now he has a new ID. Okay. You should be able to see the channels now. Okay, good. So I think now I'm still stuck here. Yeah. What is it doing now? Let me try and use Google Chrome. Yeah, I'm still stuck. Okay, let's try that one. Okay, looks like it's happy with Chrome, but not with Windows Edge, Microsoft Edge, which is weird. I assume it's some sort of caching issue. Okay, so let's take a 5-minute break until this notebook will reload, because I have to have a personal break anyway. No, I was using Microsoft Edge, which is the same engine as Google Chrome. Firefox, I think, would be, you would expect there to be more problems. Now it's running Google Chrome. Okay, so let's have a 5-minute break. Back at 5 to 4. Okay, good. So here, yes, this is an example of a not Markovian. It's not a Markovian domain anymore, because if I want to take the smoothness of the control into consideration, then it is not just the current position of the robot, but also how we got there. The history would be important. So the blue line would be much better than the red line. But then that means I cannot assign a Markov. I cannot apply the straightforward reinforcement learning theory anymore. The convergence proofs don't work anymore. That's all I wanted to say about that, basically. So what we're trying to do, I guess it started a little bit too early. A sip of water. So what is our goal in reinforcement learning then? We want to find the best policy for the agent to act. So we want the agent to choose for every state. We want the agent to choose the best action that it can. So how do I know what the best action is? And according to Lee, let me just respond that. So Google Colab works best with Edge and Chrome, not so good with Firefox. And I haven't tried it with Safari, but I think that would also be not so good. So I suggest that you use the browsers based on the, I guess it's called the WebKit engine. Those are specifically targeted towards running the Google Colaboratory notebooks. So I don't recommend using Firefox or Safari. So I want to find the best policy. What does it mean to be the best policy? Well, we need to choose for every state. We want to choose the best action. But then how do I know what the best action is. And for one thing, in our domain, often we are dealing with stochastic domains. So that means that the transitions may succeed or may fail, or there may be noise in the actuators, in the sensors. So I want to be able to pick the best action, even though there's some randomness in my domain. And also, some domains, you may end up having the best action may not be a deterministic policy, but it may be a stochastic policy. You may have to move randomly in order to get the best reward. So if you, let's say you're trying to play a game against another agent, you're trying to play soccer. If you always drive up on the left wing, then eventually the other agent will learn that that is what you do, and then will be very easy to block you. So you will need to be able to have some other actions too. You may have to make action movements randomly, introduce some randomness into your actions in order to be able to maximize your reward. So that means we're trying to maximize the expected, so that's the E here, the expected reward that we get from starting at time t equals 0 up to our horizon h. For the reward that I get moving from state st by choosing action at to end up in state st plus 1. This action is done selected by the policy pi here. So it's parameterized based on the policy pi. And here I have the discount factor, gamma to the power of t. So let's talk about the gamma. I just don't know how to type these in Unicode. So I always have to go and select them in Wikipedia page. So in our system, I want to find the policy pi. I want to find the policy pi that maximizes this expression. What this expression is the expected value of the sum of the rewards that I collect by selecting action based on this policy pi. For starting at time t equals 0 up to the end of the episode, h, up to my horizon. But the rewards are discounted by a factor gamma to the power of t. So this discount factor gamma is there because we want to, it usually is true that the earlier you can get the reward, the more useful it is to you. The less things can go wrong. So if you can win the chess match in 3 moves or 30 moves, you would prefer to win it in 3 moves, because who knows what's going to happen. Maybe you missed something in the other 30 moves, or something else goes wrong, and all of a sudden you end up not winning. Or if you think about money, if I give you, I'm not going to give you any money. If your parents give you $1,000 today, or they give you $1,000 5 years from now, then the money today would be more useful to you than the money 5 years from now, because you could invest it, you could do something with it, you can make it grow, you can start a business. So the value of the reward diminishes over time, and in fact it diminishes quite quickly. It diminishes exponentially. So gamma is usually set to something like 0.9 or 0.99, some value less than 1. If you set it to exactly 1, then there will be no discount. So then whether you get $1,000 today or $1,000 10 years from now, you don't care. That's the same. Or if you set it greater than 1, then things that you get later on are even better than things that you get now. That's usually not the right thing. That's usually not what we expect. Secondly, we want to discount. So one thing is that the discount, that gamma doesn't decrease exponentially. Gamma is a constant. But if I have 3 rewards, let me do it after this one. Yes, gamma is between 0 and 1. Including 1. Sometimes we don't want the discount factor, very rarely, but yes, sometimes you have a domain where you don't want any discount factor. In that case, you can set it to exactly 1. Then you don't have any discount. So let's say I'm in a domain and I go through various states. So here's my history. I start in state 0, then I execute action 1, and I end up in state 1, and I get $1, or I have to pay $1. And then I execute action 1 again, and then I end up in state 2, and I get $1, and I end up in execute action 2, and I end up in state 333, and I have to get $10. Right, so here's some episode that my agent was executing. So then calculate the reward for this episode using a discount factor of gamma is equal to gamma. I guess we can do that. Oh, I set gamma to 1 first, and then I just generate some states. They don't actually have to mean anything at this point, so string x, string random dot randint 0 to 10 for I in range n, and the actions. And okay, let's call it h then.
Professor, you should also modify the first line.
The first line?
Yeah, because reward.
Oh, yeah. You mean this one?
Yes.
Correct, yes. So that will be S. that state, that action, I want to move there and get the rewards of this place, and states I plus 1 plus states I, comma, actions I goes to states I plus 1 rewards I. And I don't do the last one anymore. That's just a dummy one then. So I'll set it to 6.
I think you labeled the actions with a little S on the third line.
Yeah. So I'm in state 3, I execute action 10, and I end up in state 5, and I have to pay $7. And then I execute state 5. From state 5, I execute action 4, I end up in state 4, I have to pay $25. So my agent just executed in the world, and this is what I observed, right? So this would be our history here. So now for this sample, calculate the reward for this episode. It's not an expected reward at this point because it's a single one, right? The history was selected using policy pi. Not that pi. Greek letter pi. So I have a policy pi, and now I want to evaluate it, basically. I want to see how good it is. So I run one test. Right? The agent runs for 5 steps, and first it goes starts in state S3, executes action 10, ends up in state 5, and has to pay $7. Then we're in state 5, we execute action 4, we have to pay some money. So then, given a discount of 1, what would be the expected reward of that policy pi? So let me see if there is actually a Unicode character for that. I don't even know. German letter E. Yeah, okay, never mind. Just post your answer in the reinforcement learning channel. Yeah. For this example here, or you can make up your own example if you want to. But then, of course, I can't tell you if you're right or not. But okay. imaginary real. The states are here. S7, you execute A6, end up in S3, get a reward of minus $75. Then, next you're in S3, you execute action 9, you end up in state 7, you get $77. Minus 42. Let me check. That could be right. That's probably 249 minus. I get 41, but okay. I did it in my head. Yeah, correct. Yes. Good. And then so that's easy. Sum is not defined. Huh? So now gamma is a constant. Once we pick gamma, it stays the same for the entire domain. But now let's say if gamma is 0.9, so let's do the same question. And now I set gamma to 0.8. And we ask the same question, then what would the answer be? length of rewards minus 1 minus I multiplied by rewards I for I in range length rewards minus 1. Zero, no, that would not be correct. So I guess it depends on how you look at it. First state is S7, not S4. So S4 is the last state. So WikiLeaks is basically, some rewards. .8 times 75 plus 0.8 squared times 77. No, because I said that the initial state, the first, you start in S7, then you go to S3, then you go to S7, then you go to S7, then you go to S4. And then you end up in state S5 here. But yeah. So the last step that you executed was from S4, A3 into S5. That's the last one. So that should be, yeah, no, then yours is correct. Yes. Yep. So this is correct. Let me calculate it first what it is. Well, why is the sum of the rewards? What did it generate for rewards? Yeah, the last one, whether you discount it or not, sort of is up to you. both would work, and I've seen both done by people. In our case here, in the actual formula, if you look at it, I think it's starting at 0. So the initial step is discounted not at all. Right? This would be exactly the formula you want to implement here. Maybe I have to use mp.sum. Yeah, I got 147. Oh, because I generated a new sample here. I generated a new problem here, but so the numbers will be different now. That's that, and I wanted to. So to debug my formula now, I'm just gonna make the thing a little bit easier. So now it's 1, right? Because I have 0, 0, 0, 0, 0, 1. So the discounted reward in that case is 1. If I have gamma is 0.8, then what is the expected reward? Oh, that's a list. mp.sum of this. Zero. Gamma to the power 5 length rewards. Gamma 0.8, 0, 0, 0, 0, 0, 1. So this, if rewards is 6, then this would be 5 minus 0. So that should be correct. Gamma to the power multiplied by rewards. So that should be a lot easier. GD. So gamma to the power length of rewards minus 1 minus I. So this should be the weights. So yeah, 1, 0.8, 0.64, 0.512, 0.40, 0.32 is the discount for the rewards going backwards. So the discounted reward for a t equals 0 . But here I have it the other way around, so that should be I length rewards I. But why, if I multiply by the rewards of I, how come I end up with zeros then? Oh yeah, so now it's correct, 0.3267, 0.3276, and then here we have our expected reward. Yeah, never mind. So it'll just be a long number. Or the string has to be 5.2f dot format expected reward. So I get 0.33 then for this case, and if I run it again, and in this case it's 72, and if I have a discount factor, then the future rewards are discounted. Then I end up with negative 1.48. If you look at that's because the negative 36 here hurts a lot, right? And the negative 67, they are closer than all of these ones, 70, 23, 57. So their value will be discounted for the current state. So now that would be one history. If I have multiple histories, that's why we calculate the expected reward. Because we run this not just one time, but we run the experiment many, many times. Yes, yes, gamma will decrease exponentially. Not exceptionally, exponentially. But yes. So that is a severe discount on future rewards, right? That's quite a high penalty for states that you reach just 5 or 6 steps further back. If you have a look at it, yeah, we have to deal with the expected. Let me just finish that slide. We have to deal with the expected reward because we run this over multiple episodes. So we try the same policy over and over again, and then we see what result we get. And here, just to make sure that what is this? Oh, 50, 50 is equal to XS 0.8 to the power XS. I'm not sure if that works. Bah, NumPy for the win again. And okay. So we have distance to state, set label, draw it all. This is what the chart would look like for gamma equals 0.8. YS line width label is equal to F that's the gamma. So here you can see the effect of the different discount factors. If gamma is 1, then there's no discount. It's just every reward is equally valid. If gamma is 0.99, then it decreases like that. So after 50 steps, the reward is discounted by about 30%, right? If gamma is 0.9, then yeah, watch out. After 20 steps, it's only worth 10%. After 50 steps, it's basically 0. And the other ones decrease even faster. right? So that's what you can select with your discount factor. And then just to make sure the expected reward, we run this over and over again, and then we calculate the average, the expected value of that reward, because we have an active agent, an active policy that picks our actions. And what we're trying to find then is this particular policy pi. The policy is a function that chooses an action, so it returns an action for each state S that we're in. So the input is S, and the output is an action A. That's only possible because the domain is Markovian. So I only need to know the current state S. I don't need to know. I only need to know the current state S in order to choose an action, because the domain is Markovian. But if you do want to, let's have a look at the grid world again. If I do want to do something like, I don't know, I only want a maximum of 3 left turns, for example. That's something that I couldn't do with the Markov, wouldn't be a Markov property, right? Because if I do the third left turn and I want to give a reward of minus 100, then in order to be able to give that reward, I need to know how often I turned left before. But nothing stops me from having a more complex state representation. So in that case, I would have to then expand the representation of the states. So instead of just having A0, 1, 2, 3, 4, B0 to 4, C0 to 4, and D0 to 4, I then have to have a augmented state representation where I'm currently in state B1 or I'm currently in state C1 and I've turned left 1 time, right? So I can make the state more complex, and in that case it would be Markovian again. But that I need to do manually. There's no automatic system that I do. It would not be the most intuitive straight representation for grid world, right? When you look at the grid world, you think the state of the agent should just be the row and column that the robot is currently in. But if you have a non-Markovian domain, so you want to learn, but you really don't like left turns, or movement left. You don't like to move left. In that case, or you like to move left, but maximum 2 times, not 3 times. Right? Then you would have to count how many left steps you've already done. But you could easily keep track of that and then make it a more elaborate state representation. Okay, so here's our discount factor, and this is what reinforcement learning is all about. We're trying to find pi to maximize this value, the expected summed up discounted reward. That's at the heart of reinforcement learning. Given the set of states, the set of actions, and the transition function. Okay, good. Then that's it for today. Next week, I think, is a holiday. So I will see you guys again 2 weeks from now. So next class will be Monday, 18th October. I'm not sure if that class will be face-to-face already. I will post a message beforehand, and I will also make it accessible via Discord. So even if it's a face-to-face class, we will still broadcast it via Discord. In the Google, in the course page. I'm just typing it now. That has a link to the Jupyter Notebook, the directory with all the Google Colab notebooks that I was working on. The links to those notebooks for this class and previous class are in the Discord chat history. Okay, you're welcome. Okay, then bye-bye. So, Jewel, how is quarantine? Are you in quarantine now?
Yeah, I just arrived 2 days ago.
Okay, okay. Another 12 days to go, I guess.
That's right. It's actually pretty cozy, pretty clean. So.
Okay, okay. Well, there's nothing you can do, so might as well just accept it.
Yeah, right.
Yeah. I know some foreigners, they posted that they left the hotel at 0001 on the day that the government told them they can actually leave the quarantine. They would wait. They would wait downstairs. They would wait in their room until 1 minute after midnight, and then they would rush out finally.
Because then you still have to isolate for another 7 days after that.
True. Yes, I'm not sure whether what they did was legal or not. I also thought it was a little bit of a overreaction. Like I would have at least slept through the night. Like
yeah, slept through the night for sure.
Yeah. Okay. Anyway, good luck.
Thank you.
If you get bored, you can do some reinforcement learning projects and read the lecture slides and stuff.
All right, I will.
Okay, bye-bye.